Hi everybody, so this is our first video in class, and today we're going to be talking about calculating net force. So we will be doing videos like this so that we don't have to spend class time with me just talking for an hour, okay? Hopefully this video will not be an hour long. If you need to pause or rewind so you can rewatch one part, you absolutely can. Do what you need to do to be successful. And you need to write down the information on the slides into the notes page that I gave you in class. So you do not need to write a whole bunch of information in your notebook. You can if you want to, but just make sure you fill in that notes page that I gave you in class and you'll be good to go. So we're going to talk a little bit more about calculating net force today. Okay, so our essential question, let me move my video so I'm not blocking the words. Well, we'll do the best we can. So our essential questions for today's lecture is how is net force of an object shown in horizontal or vertical direction using diagrams. So remember that the word horizontal means side by side and the word vertical means up and down. And how do we determine if the forces are balanced or unbalanced? And then think about, here's a share what you already know about the essential questions. So think about those questions and just think about the things you already know. I'm not going to make you write those down. Okay, so a force is a push or a pull that causes an object to stop, move, or change direction. So something is sitting still, so like my phone is sitting still, and I'm going to push it, and it's going to start moving. It could already be moving, and then I stop it, so that's a change. So it might stop, it might start moving, or instead of going up and down, maybe it's going left to right. So any sort of change in its motion is created by a force. And scientists use arrows to show the direction of each force acting upon the object. And we will talk about those diagrams in a little bit. If you hear the thunder in the background, it's because it's getting ready to rain. I apologize. So here on the side, it says list one example of a force from the picture above. So there's this guy who is pushing on these blocks of wood, I guess. So what is one force that is happening in this picture? There are several different examples. Just make sure you think of at least one. So a brain break. So think of examples of a push or pull that is used in daily life. And you can create a short list of push or pull examples and label it as a push or pull. We don't have partners because you're doing this at home, so you just might want to share your list with your friend when you come to class or share it with me. A pull I can think of is when I'm walking my dog, sometimes he will see a bird or a person and he will pull on his leash and try to pull me towards whatever he is excited about. So that's the force that I think of right away because he does that almost every day. All right, so balanced forces. When an object experiences balanced forces, the object does one of two things. It either stays still or it continues to move at the same speed and in the same direction. So please keep in mind, balanced forces does not mean there's no motion. Balanced forces means there's no change. So if it's staying still, like my phone, it's going to stay sitting still, like nothing is changing about its motion. If it's moving to the right at 10 kilometers per hour, it's going to keep moving at that same speed and in that same direction. So balanced forces means no change in motion. Let me see what's behind me over here. So we have these two guys. They are pulling on the rope, doing tug of war. They are pulling in opposite directions in the same amount of force, and so nothing's going to happen. They're not going to go anywhere. And so how would having balanced forces affect an object's movement? And the answer is it won't. It won't affect the movement at all. It will stay completely the same. Let me put myself back over here. All right, so examples of balanced forces. So objects at rest. So these cars are in a parking lot. Do you guys call it a parking lot or a car park here? I don't know. In America, we call it a parking lot. So these cars are parked. They're sitting still. They're not moving. Nobody's driving. They're just sitting there. This cup and saucer are just sitting there. This dog is not moving. So he's not running anywhere, but is he actually completely at rest? Well, no, because his heart is beating, his lungs are breathing, but technically he's not completely at rest, but for our purposes he is, because he's not walking anywhere. Here we have an example of somebody riding a horse, and if it's balanced forces, they're going to keep moving in that same direction at the same speed. And then here we have a pretty sweet little blue car, and you're going to keep driving to the right at 20 kilometers per hour, maybe. So again, balanced forces just means there's no change in the motion. Okay, so here we have several people who are doing tug of war, and this is an example of a free body diagram. And so we have the two objects, so the two different groups of people, and then we have the direction of the forces and the magnitude. So magnitude just means how strong they are. So we have one force to the left of 17 newtons, we have one force to the left of 25 newtons, and we have one force to the left that's 13 newtons. Then we have one to the right, that's 15, one going to the right that is 30, and one going to the right is 20. And if you notice, these people are not going anywhere. They're just standing still, kind of. And it's because if you add 17 plus 25 plus 13, you get 55 newtons pulling to the left. And if you add 15 plus 30 plus 20, you are also getting 55 newtons to the right. So we have 55 to the right, 55 to the left. Since they are moving in opposite directions, we subtract them. 55 minus 55 is 0, and so there's a 0 net force. So nothing about this group of people is going to change. They're going to stay in the exact same spot, and nobody's going to be able to win. So another example is if you maybe put a pencil on your desk. So I'm going to use my marker here, and if one person pushes and one person pushes, if you're pushing with the same force, then nothing's going to happen because we have balanced forces. And you have two people who are moving with about the same force but in opposite directions. They cancel each other out. So the person on the right, their force doesn't change anything. The person on the left's force doesn't change anything. And it's because they are working in opposite directions with the same amount of force. So now we'll talk about unbalanced forces, which is the opposite. A lot of times in science, we talk about one thing and then we learn about its opposite. So when we have unbalanced forces, when unbalanced forces act upon an object, they always cause a change in motion in one of these areas. And it could be one of these three, it could be all three of these things. So the position, where the object is located, will change. So my marker's over here, and I'm going to put unbalanced forces, and now my marker's over here. So it changed positions from one spot to another. The direction of motion could change. So my marker is moving to the left, and then I'm going to change force, and now move it back to the right. So that was an unbalanced force because it changed direction. And then speed, also, you could be going really slow, and then maybe you got excited about something and you speed up. So it could be any one of these things, or any combination. You can move from this place to this place, and you can do that by moving slowly and then really fast. So there we change the position and the speed. We could change the position and the direction. So maybe our object is going from down here to up here. You could change the direction and the speed, or you could change all three. So we're changing the position, the direction, and the speed. Okay, so again, with these three, it could be one of the three, it could be two, it could be all three. It depends on what forces and what the amounts of them and what directions they're going in. So here we have somebody who's sitting on a skateboard for some reason, and their friend is pushing them. And so what direction do you think the skateboard will move, and why? So this guy is sitting on the skateboard. What direction is he going to move in? He's going to move to the left because his friend is pushing him to the left, and there's nothing pushing him back to the right. So the force moving to the left is going to win, and that's the direction he's going to move. So other examples of unbalanced forces. So objects that are changing direction. So if you look here, we have a force that is moving to the right with 10 newtons, but we have a force that's moving to the left with 20 newtons. So we have forces moving in opposite directions, but the one moving to the left is stronger. So this object, what is this object? What does that say? Moves left, moves left. So say this is like a person or a car or a box or something. Because the force moving to the left is stronger, it will move to the left. Here we have this child in this car. So this boy is pushing this other little car, this other little boy in a car. And so the child in the car would move in the direction of the push. So he is pushing his friend or his little brother to the right. So this little boy in the car is going to move off to the right. And now we have another group playing tug of war. And the group exerting means like to use or to do. So the group doing the strongest force will determine the direction of motion for the rope. So I'm going to guess, it's hard for me to see, there's no numbers on this one. So there are 3 people on this side, and they look like they're all pretty strong guys. And then there's 1 person on this side. So all these arrows showing all this motion to the left, and there's this 1 or 2 little tiny arrows going to the right. So there's way more force pulling to the left than to the right. So these 3 guys on the left are going to win because the rope is going to go off to the left. Okay, so let's see what this one says. So in a classroom experiment, students explore the impact of different forces on the motion of a pendulum. So a pendulum is something that swings back and forth like that. The students formulate a hypothesis. Hopefully we know what a hypothesis is. If we increase the force applied to push the pendulum, then its motion will increase. As they gather data, they construct theories to explain observed patterns of motion. How do hypotheses, theories, and laws differ in their roles of explaining the behavior of the pendulum under different conditions? So basically, like, what could they do to show how the force affects the pendulum? So if you have something that is just swinging, it could be a necklace too, right? Like something that's swinging, how could we show how forces might affect how the object swings? Okay, so more about net force. I'm going to keep moving myself around. Can I move that down? I don't ever like it when they have the drawing tools like that. Okay, so the net force is the overall forces acting on an object. It is measured in newtons. How much is a newton? It's just the unit we use. So instead of using kilograms or millimeters or degrees Celsius, we use newtons when we talk about force. And a net force always includes a direction. So your net force should be a number and a direction. So 10 newtons to the left or 30 newtons south. Okay, so always a number and a direction and your unit. So scientists use arrows to show the direction of each force acting upon the object. So here we have these ladies pushing a car. I've been there. Is the car moving away from the women or towards them? What do you guys think? We're going to assume that the car is turned off, right, for safety's sake. But is the car moving towards them or away from them? Well, we would hope that they are pushing it down the street, so it should be pushing away from them because they are all pushing in one direction together, so it should be moving with a force away from them. If there was somebody on the other side pushing in the opposite direction, then they may be able to slow down the motion of the car, and they'd just be really rude too. That would not be nice. All right, so let's talk about how to calculate net force. So objects move in the direction of the greater force. So whichever force is bigger wins. When more than one force acts on an object, they can be in the same direction, and so the object would move in the direction of the force, or in different directions, and the object would move in the direction of the larger force. So if we have like 3 people pushing on this marker, and they're all pushing to the left, then our marker will, of course, move to the left. But if we have 2 people moving to the left and 1 person pushing to the right, then it depends on who is stronger. If the 2 people combined have more force, then it will still move to the left. Okay, so net force. To calculate the net force, if the forces are going in the same direction, you add them. So here we have 30 newtons and 20 newtons. So what is the net force that is being applied to this box? So same direction, we're going to add those numbers together. So we have, is that 30, 30, and 20. We're going to add those together. So the net force on this box is 50 newtons to the left. Because remember, your net force always has a number and a direction. So 50 newtons to the left. So this box would definitely move to the left. And if you think about it this way, if they're moving in the same direction, these two people or these two forces or whatever they are combining their efforts, like they're working together. And so you want to add their forces together to see what the total amount of force is. But what if they are going in opposite directions? It's a good question. So to calculate the net force, if the forces are going in different directions, you subtract the forces. And so the direction of the greatest force would be in the direction of the net force. So in this one, so when they're moving in the same direction, they are working together. But when they are moving in opposite directions, the forces are working against each other. And so we need to cancel out whatever is in common, and then whatever is left over is the actual force, and the direction of that force is the force that wins. So here we have 20 newtons moving to the left, and we have 30 newtons moving to the right. So we are going to subtract those two. 30 minus 20 is 10, and the force on this side is bigger, so this box is going to move to the right, but only with a force of 10 newtons, because 20 newtons of the force on this side had to be used to cancel out the force on this side. So all it has left over is 10 newtons to move it. So it's not going to move probably as fast as the box in the previous slide. So again, opposite directions you subtract, same direction you add. All right, so here's just a quick kind of check for you. So without considering other forces such as friction, we talked about friction yesterday, which is when two things rub together. We're not going to worry about that because that makes our calculations much more complicated. What is the net force in this box? So we have 20 newtons to the left, 30 newtons to the right. What do you think? They're moving in opposite directions. So are we going to add or subtract them? What do you think? So they're opposite directions, so we're going to subtract. So we're going to subtract 20 from 30, because that's the smaller number into the big number. So the amount of force is going to be 10 newtons. Remember your label always. So 10 newtons. So we have 30 minus 20. And then the other question asks, which direction will the box move? Will it move to the left? Will it move to the right? Well, since we have more force moving to the right, that's the direction our box is going to go. 20 newtons from this force is going to be used to cancel that out. And so what's left is 10 newtons moving to the right. Move me again. Okay, so what forces act on objects? So the interesting thing I think about forces is that it's never just one thing. So a lot of our diagrams will be very simple. It'll show a push to the left, a push to the right, and that's it. But in the real world, it's never that simple. So here we have gravity. So gravity is why objects fall to the ground when they are dropped. You've known that for a long time, right? So gravity is always going to pull things in. So gravity pulls things into the center of mass. On Earth, that just happens to mean that it just moves down. So the gravity pulls it down. Here, this table is touching the book bag exerts the normal force, which here says it's the push a surface gives to support an object resting on it. So again, like my marker, if I have it on my desk, the desk or my hand is exerting the normal force. So gravity is trying to pull this marker down, but my hand is like, we're gonna hold this marker up, we win. So right now the forces are balanced because the marker is not moving. Then I'm gonna move my hand and gravity wins. So that's why it drops down. So gravity is the downward force that pulls objects toward the earth. Gravity pulls things in. Normal force is the push a surface gives to support an object resting on it. And objects are held in place by normal force and kept on earth by gravity. So they're in a balance together most of the time to kind of keep things in place. Let's look at what this question says. How do normal force and gravity keep your book in place on your desk? What do you think? So it's very similar to the backpack, just with a book instead. All right, let's see what's next. So calculating net forces. So we're just gonna go over this a couple more times. So box A, which is here, has 25 newtons pulling up and 5 newtons pulling down. Again, since these are opposite directions, we're going to subtract. 25 minus 5 is 20. And the direction it moves is whichever force is greater. So this one is bigger. That box is going to move with a force of 20 newtons up. So then we have this one. We have 50 newtons to the left. We have 25 newtons to the right. Opposite directions, so we subtract. 50 minus 25. Our answer is 25. And then which direction? This side has the bigger force. So this box is going to move with a force of 25 newtons to the left. All right, so connecting motion to net. So the mass of an object can determine its force. So objects with greater mass will have more force than smaller objects, even if they're moving at the same speed. So if you have a little tiny sports car and you have a great big truck, and they're both going down the road at 70 kilometers per hour, the truck, just because it is so much bigger, has way more force than the small tiny car does. If they were to hit a wall or get into an accident, the truck is going to be way more damaged than the little car, just because it has way more force behind it, and it would take a bigger force for it to stop. So objects with greater mass will have more force than smaller objects, even if moving at the same speed. Whichever one is bigger wins. So for example, hitting a nail with a hammer has less force than when hitting it with a mallet. So a hammer is this one. It is a little bit smaller, so it has a force, but not as much as this bigger mallet does. So this would be like the little sports car. This would be like the big Mack truck. So why might a ball go faster when hit by a bigger metal bat than with a plastic toy bat? What do you think? Because the metal bat has more mass. So when it hits it, it exerts more force. Okay, so whichever one is bigger wins. So let's think about this one. 3 forces act on an object. One force pulls right with 60 newtons. That's this one here. The second force pulls left with 30 newtons. That's here. And the third pulls left with 20 newtons. What direction will the object move? So here's where we have an example of more than just 2 simple forces working together. Here we have 3. What do you think we might do to figure out what the net force is of this whole box? What do you think we might do? We need to do 2 different steps. So we are going to add the forces that are going in the same direction because they are working together to pull this box to the left. So we have 20 and 30. So we have 50 newtons total on this side pulling to the left. And then we're going to subtract that combined from the opposite direction. Because remember, if they're moving in opposite directions, we subtract. So we have 50 newtons to the left. We have 60 newtons to the right. 60 minus 50 is 10. So the net force on this whole box is 10 newtons. And it's going to move to the right because it has just a little bit more force on this side. Okay, so even though there were 2 forces working on this side, their numbers combined weren't strong enough to win compared to the 60 newtons. Okay. All right, so here we have a similar one. So again, we have these 2 on the left, and we have this 1 on the right. And we are going to combine these 2 on the left because they are working together. We have 10 newtons and 20 newtons. So moving to the left, there's a total of 30 newtons. And then we have this one on the right, which is 5 newtons. So we are going to take 30 minus 5, because again, they are working against each other. 30 minus 5 is 25 newtons. So 25 newtons is the force of the motion. And it will be moving to the left because this side of the box has more forces on it. So 25 newtons to the left. So think back to the last time you rode a roller coaster or amusement ride that made you feel weightless. So it made it feel like you were floating. Use your knowledge of forces and think about why that might happen. This was the last time I rode a roller coaster at Disney World. That's what it was. It makes you feel like you're floating. Why might that be? All right, so here we have a few more examples. I'm just going to go through these quickly. You need to make sure that you calculate this on your own and get it written down. So box 1 has a force, sorry, this is so small, has a force pushing to the right with a force of 25 newtons and a force moving to the right with a force of 25 newtons. So what would the net force, the number, and the direction on box 1 be? Box 2 has, is that 18? Sorry, 18 newtons to the right and 25 newtons to the left. So what would the net force and direction of box 2 be? So we have 14 newtons pushing down and 36 newtons pushing down on box 3. So what is the number and the direction of its net force? Box 4 has 25 newtons pushing up and, sorry, it's so little, does that say 8? 8 newtons pushing down. So these are moving in opposite directions, so what math would you do? What would the net force on this box be? And then box 5, we have 25 newtons to the right and 65 newtons, it's a big one, to the left. So what would the number and direction on box 5 be? Because remember, they're moving in opposite directions. What kind of math do you need to do? And then here, it's just a place for you to write your spots. I believe that's on your notes. Okay, so a couple more things. So how is net force of an object shown in a horizontal or vertical direction using diagrams? So write down or think of how have we shown in this, on these slides, how have we shown the different forces? What do we use? And then how do we determine, how do we figure out if the forces are balanced or unbalanced? Okay, so what do we do? How do we figure it out if they're balanced or unbalanced? If you still have questions, you can write these in your notes. You can also let me know. So let me go back here because there's one thing I want to point out. Okay, so balanced and unbalanced, right? If the net force is 0, it is balanced and nothing changes. The speed doesn't change, the direction stays the same, the amount of force stays the same. The direction, position, and speed all stay the same. If it is 0. If it is anything else, any number, it is unbalanced. So if it is 1 net force, if it is a billion net force, doesn't matter. Something's going to change. We just need to figure out what it is. 0, balanced, any other number, unbalanced. And that's a quick way for you to be able to tell the difference. Okay, so that's the end of our notes. If there was anything you missed or you didn't understand, you can rewind and watch it again. As always, you can email me, you can ask in class. Make sure you get your questions answered. Okay? See you guys in class.